Thanks for Alexander and Charlie for inviting me. I was going to give kind of a generalist talk on resource theory, thermodynamics, and possible applications to black holes. But we can kind of go. I can kind of go in any direction. I hadn't fully plotted things out. And apologies, especially to Henry for sleeping in. I haven't managed to sleep in past 5:30 for the last 2 weeks, and I'm happy to report that I did this morning. Can I just ask a quick question? How many people are familiar with resource theories? And how many?
I think I'm familiar with it, but maybe not under that name.
Yeah. What name?
I don't know. It has
Okay. Yeah. So I guess I wanted. So I thought I would talk about this in part because I think Charlie, from the very early days of entanglement theory, kept kind of pressing that entanglement is a resource, and people at the time were kind of noticing all these similarities between thermodynamics and entanglement, or privacy and entanglement, and there were all these things here. So at some point, a few of us formalized the notion of a resource theory and proved some theorems about them, and so although I'll be talking about thermodynamics, it's kind of in a more general context where you can apply these results to many other so-called resource theories. So what I'll do is I'll just give kind of a quick intro to resource theories and thermodynamics. And then maybe I'll talk about, so far most of the talk of resource theories is about a single resource like entanglement or coherence. I'll talk about multiple resource theories. So we kind of, in resource theories, we often have something which I sometimes like it's kind of like a bunch of second laws, like that the entropy has to increase as a second law, but there's generalizations of that for other resource theories. Entanglement only decreases is another example. For multiple resource theories, you have a first law. It's kind of a generalized first law for multiple resource theories. And again, an example of that is thermodynamics, where we have work and heat. And I guess a nice, the kind of simplest example of that is Landau erasure and Maxwell-Demond, where you use a heat bath to convert one resource to the other. You're converting, entropy to work, or work to entropy if you're erasing or if you're extracting work. So kind of the first law tells you about multiple resources and how you convert one to the other. So I'll talk about that, but not just in thermodynamics, because you already know probably thermodynamics, but in a generalized setting. And then maybe I'll talk about the resource theory of thermodynamics for closed systems. We've tended, in at least the formal resource theoretic approach, we tend to talk about systems in contact with a heat bath, so the open system approach. But I'll talk about thermodynamics for closed systems, and the reason we did that actually was, well, A, because we wanted to do that for a long time, but B, because we wanted to apply it to conformal field theory, so or in the context of ADS-CFT. So if you want to understand, say, well, we're interested in the question, so I'll just say, you'll see that when we talk about resource theories in thermodynamics, there's not just one second law, but there's many second laws. It's not just the free energy that decreases or the entropy that increases. There's a whole bunch of quantities which also have to go, which are also monotonic, which also go down or up, depending on how you define them. So there's many second laws, and so you could ask the natural question to ask.
It's not just sort of trivially related to Legendre transformation, like free energy.
Yeah, free energy and entropy is trivially related.
Yeah. These are interesting other ones, or more interesting other ones.
Yeah, there's more interesting other ones, like all the Renyi divergences give you constraints on evolution, so they're like a second law, because the second law is a constraint on your evolution. It tells you that under thermodynamics, you will, your box of gas cannot go to any state. It'll go to a state where the entropy is larger. So So second laws provide constraints on transformations. And so we find that there's a whole bunch of other constraints. So we call these many second laws. And then you can ask, the natural question to ask is, for black holes, do these additional second laws play a role? Do they provide constraints on black hole evolution, for example? And I think for that, so I'll try and at least get to that. There's some nice things that arise from my point of view, in the sense that one often computes for black holes, for example, you can compute the free energy by looking at some path integral. And here we find that we can compute the Renyi divergences by looking at the path integral of a quench. So there's some cute little, some nice little things here. But I would say, so many second laws for black holes. I would say really we're just able to ask the question rather than answer it. But make some progress in answering this question. I guess we would say, if you believe in ADS-CFT, there are many second laws for black holes. That's clear if you believe in ADS-CFT, but what they correspond to on the gravitational side is something we're not able to answer. And that, I think, is we more just want to get that question out there, I guess. Okay, and I guess the style will just be just ask questions without putting your hand up and interrupt me. Okay. Any questions about the direction that I'll go in?
I think I need to wait and ask it later, but just so you know, it's on my mind.
Yeah.
So I think of a CFT as a sort of fundamental microscopic unitary thing.
Right.
And I think of a second law as a emergent thing that's
Yes.
not always true.
Right.
So I'm very curious about these extra second laws and how they reside in that.
Okay. I would agree that they're emergent. I'm not sure if I would agree that they're not always true, but one has to be precise. One has to be precise about the conditions under which you can claim a second law. And you might want statements like "for almost all times" or something like that.
But I think for second law, if you can reach equilibrium, then it's gone. And in cosmology, so there's a whole question of what.
Good.
Okay.
I'm glad you asked.
That's all I meant, actually.
Right. So our many second laws, we will see that that there's only one for thermal states. But if you have a state which is out of equilibrium, then these many second laws place additional constraints. And so the question is, for out of equilibrium black holes, do they impose additional constraints?
I like to use the term temporal provincialism. We're so used to having a second law, we assume it's always there. But
right.
in cosmology, when we're trying to understand the origin of the beginning, we should at least keep track of what we're putting in.
Good.
And what we're getting out.
Yes.
And it can get ropey because we're so used to having a second law for free.
Right. And I totally agree with that. And I think one of the goals of kind of the resource theory approach is to put thermodynamics and other resource theories on a very firm mathematical setting, where you're, like when I learned thermodynamics, it was just a bunch of facts about boxes of gases and PV equals nRT and stuff like that. And here you are basically saying, and I was never told what the rules of thermodynamics are, what is the experimenter allowed to do, and so the goal was kind of, let's put it on a very rigorous setting. And other approaches have done that as well, but you want to put on say what the experimenter is allowed to do and then derive.
But it sounds like you're setting this up in a situation where you absolutely have a second law of thermodynamics. Or at least when you say out of equilibrium, are you going to ever consider it in equilibrium?
It's a special case.
So, okay, anyway.
Yeah, let's get there.
If you wanted to get to that, don't slow him down so he stops.
Yeah, exactly.
Okay.
Yeah.
I'll
done.
I'll have it'll be a slight problem that if I'm going to be very detailed and rigorous, then we're not going to get very far. But I'll also probably provoke lots of arguments by doing that. But I'll try and kind of skirt that line. But feel free to ask for clarification.
Please try and get to point 4.
Yeah, good. Okay, please try and get. Okay, good. So, I mean, I could. Okay, I'll make sure I get to point 4. I have until.
Maybe, I think at most at 12:15.
Okay, I'll try and go. I'll try and keep it to an hour. I'll try and keep it to an hour. Okay, good. I will keep it to an hour. I won't. Okay. So resource theory. So we formalized it as follows. Well, I guess that you want to prove. So you have the following. You have a class of operations, C, which is a subset of the completely positive trace preserving maps. So some subset of CPTV maps. So in other words, you have for some reason a restriction, like under LOCC, you can only perform local operations in classical communication. In thermodynamics, one has a restriction like you have to preserve energy and you can't, there's, maybe there's restrictions on that. For thermodynamics, there's also resource theories of coherence or of asymmetry, like you have some kind of conservation law or symmetry in your theory and you can't do any operations which aren't covariant with respect to that symmetry. So you can't do everything because of some super selection rule, for example. So you somehow have a restriction on what you're allowed to do. And under that class of operations, you're usually allowed to, there will be a set of states you can create under that class of operations. So there's some set S. We used to call that the free set, and we'll see that when we get to multiple resource theories, we should we realize that we've formulated resource theories incorrectly, and we should no longer refer to that as a free set of states. So an example of the free set of states is in entanglement theory, all the separable states are for free because you can create them under local operations in classical communication. In thermodynamics, the free state you could imagine is the Gibbs state, the thermal state. So you could even define thermodynamics to be the set of operations which preserve the heat bath at temperature T. I can just define thermodynamics to be that. That's one definition of thermodynamics. Jess?
Oh, just a question. So CPT map already, you're picking a direction in time, right? And that's fine. It's just I want to make sure that the resource theories framework has that directionness in time.
You're talking about transforming one state to another, and the reverse may not be possible. Yeah,
Right.
That seems totally fine. It's
Okay.
very useful. Most of our experiences are.
Yeah. I'm not so sure. I think if I do a pre and post, again, I often think if I do a pre and post selection, I maybe, and I do a CPTV map in between.
CPT maps are definitely time asymmetric, right?
But if I then add post selection on top of that, then I think I may be able to define the resource theory where you have time symmetry. Maybe that's an interesting resource theory we could study. Okay, anyway. So CPTV map, so set of states, example, separable states, thermal states for thermodynamics, some examples, the maximally mixed state. So the identity over D is one for the resource theory of purity. So anything which is not maximally mixed has the resource of purity. Energy, the resource theory of energy, so the ground state is for free. You're given the ground state, but any other state which is excited or has energy is a resource because it has more energy than the ground state. So that's the resource theory of energy. This is the resource theory of entropy. Incoherent states, so states which, etc. Any questions about defining resource theories? Okay. And so what we showed at some point is that under certain not so interesting assumptions, there's a quantity called the relative entropy distance, which is given by between rho and sigma. Those minus, so trace of rho log rho minus trace of rho log sigma. And if I look at some measure which are defined to be the infimum over all sigma in my set of free states, I call S, then this monotone here is if my theory is reversible, then this this is a monotone, so this gives a second law. And in fact, if I can consider other measures besides the relative entropy, like the Renyi divergences. So if I have any measure which is contractive under CPTP maps, in other words, goes down under CPTP maps, then this thing gives you second laws.
And these multiple second laws, right? I know for density matrices and CPT maps, you can summarize this all more compactly by talking about this mixedness increasing or majorization.
Yes.
So are all of these things, can they be expressed in that way, or are there like additional second laws that can't be thought about as a result of majorization?
Yeah, I don't. So the Renyi divergences are just a kind of a catalytic, like a reversion of major. They're kind of stronger than, provide stronger constraints than majorization. So they're not quite equivalent.
Really?
So